Non-parametric test. Non-parametric tests are a class of statistical methods used when the data do not meet the assumptions required for parametric tests, such as normality or equal variances. Unlike parametric tests that rely on numerical values and distribution-based calculations, non-parametric tests are based on ranks or medians and make fewer assumptions about the data's underlying distribution. These tests are especially useful when dealing with ordinal data, skewed distributions, or small sample sizes. Common examples include the Mann-Whitney U-test, Wilcoxon's signed rank test, Kruskal-Wallis test, and Spearman's rank correlation. Because of their flexibility and robustness, non-parametric tests are valuable tools in real-world data analysis, particularly when data conditions are not ideal for traditional parametric methods. Welcome to today's session on non-parametric tests. By the end of this session, you'll walk away with practical knowledge you can apply in real-world analysis, especially in cases where your data doesn't meet the assumptions required for parametric tests. What will we cover? We'll explore three key non-parametric tests, each serving a specific type of analysis when dealing with ordinal data or interval Bach ratio data that doesn't follow a normal distribution. Topics: 1. One sample sign. Test O used when comparing a single sample median to a hypothesized value. Second Mann-Whitney U-test. O, a powerful alternative to the two-sample t-test when comparing medians of two independent groups. 3. Moody's median test. O helps us compare the medians of two or more groups to test whether they come from populations with the same median. In this slide, we're focusing on three essential non-parametric tests, which are valuable tools when your data does not follow a normal distribution, something we frequently encounter in real-world projects. Key principle: if your project Y, response variable, is not normally distributed or has outliers, then a non-parametric test is more appropriate than a parametric test. Let's look at the three main tests covered here. 1. One sample sign test. Use this when you want to test whether the median of a single sample is equal to a specific target or benchmark. Example: checking if the median handling time in a process is meeting the target of 6 minutes. Second Mann-Whitney U-test. This is used to compare the medians of two independent groups. It's the non-parametric alternative to the two-sample t-test. Example: comparing customer satisfaction ratings between two stores. 3. Moody's median test. Use this when comparing the medians of more than two groups. Unlike ANOVA, which compares means under the assumption of normality, this test works with medians without requiring normal distribution. Example: comparing median salary across three departments. These tests help us make confident decisions even when our data is messy or doesn't meet parametric assumptions. So always remember: test normality first. If it fails, come back to this slide and choose your test accordingly. This slide introduces the concept of non-parametric tests and highlights when and why we use them. What are non-parametric tests? Non-parametric tests are statistical tools used when we cannot assume a specific distribution for the population data. Unlike parametric tests, which assume normal distribution and focus on means, non-parametric tests work with medians, ranks, or signs, making them more flexible. They are particularly useful in the following situations: when the data is ordinal, ranked like satisfaction levels: poor, fair, good, excellent. When sample sizes are small, making normality assumptions unreliable. When data violates the assumptions required for parametric tests, such as unequal variances or non-normality. When to use: you should consider non-parametric tests when the data is skewed or fails the normality test. You are using ordinal or ranked data, not interval or ratio scales. Parameter estimates like mean or variance are unreliable due to data irregularities. You want a robust test that is less sensitive to outliers or non-normal distributions. To summarize, when in doubt about normality or when dealing with ranked or small sample data, non-parametric tests are your go-to tools. We'll dive into specific examples shortly, like the Mann-Whitney, Moods median, and one-sample sign test. Let's now discuss the one-sample sign test, one of the most commonly used non-parametric tests. What is the one-sample sign test? This test is used to determine whether the median of a population is equal to a specific hypothesized value. It is the non-parametric counterpart of the one-sample t-test and is ideal when your data is not normally distributed, or there are extreme outliers. The measurement scale is ordinal, such as satisfaction ratings or rankings. You only care about whether values are above or below a benchmark, not by how much. In other words, this test ignores the magnitude of the differences and just considers the sign, whether the data point is higher or lower than the reference. When to use it? You should consider the one-sample sign test when you're testing if the median equals a specific benchmark. For example, checking if the median turnaround time equals 5 days. You're working with paired data, each observation compared against a fixed reference. The data is ordinal, skewed, or contains outliers that make parametric assumptions invalid. This test is especially helpful in business situations where responses are ranked or subjective, like customer satisfaction surveys. Or the data doesn't follow the ideal bell curve, which is often the case in real-world process data. This makes the one-sample sign test a robust alternative when you can't use a TD test due to assumption violations. Before using the one-sample sign test, it's important to ensure that certain assumptions are met. Let's look at the 3 key assumptions. 1. Observations are independent. This means that each data point should not influence the others. For example, if you're collecting feedback from customers, one person's response should not bias another's. Violation of this assumption can affect the validity of the test. 2. Data is at least ordinal. The sign test does not require normal distribution, but the data must be at least ordinal, meaning the values can be ranked in order. For instance, satisfaction levels or rating scales are acceptable because they represent ranked data. 3. Only the sign of the difference matters. The test focuses solely on whether the observed value is above or below the hypothesized median, not by how much. It doesn't consider the magnitude of differences, only their direction, positive or negative signs. These assumptions make the one-sample sign test a very flexible tool, especially useful when traditional parametric assumptions like normality or known variances are violated. Always check these assumptions before proceeding to ensure that your conclusions from the test are statistically valid. Let's look at some practical examples to understand where we can apply the one-sample sign test. Handling time, HT. Suppose we've implemented a process improvement initiative to reduce handling time. Now we want to test if the median handling time after the change is less than 10 minutes, which was our old benchmark. In this case, we're comparing the current data to a known target, ideal for a one-sample sign test. Collections. Let's say we're tracking monthly collections after a new billing system has been introduced. We want to test if the median monthly collection now exceeds $100,000. Since we're comparing the new data to a fixed target, again, the one-sample sign test is appropriate. Cycle time. This is similar to the collections example. If a process improvement aims to reduce cycle time, and we want to check if the median cycle time now beats a previously set benchmark, we can use this test. Production in kg. Here, we want to validate whether the median daily production is greater than a specific target. Let's say 1,000 kilograms per day. If the data distribution is skewed or has outliers, the one-sample sign test becomes a better choice over a parametric test. The key message here is, use the one-sample sign test when you're testing against a known standard or target, especially when your data may not be normally distributed, or when only the direction of change matters. Now let's understand the one-sample sign test and its role in Six Sigma projects. This is a non-parametric test used to evaluate whether the median of a sample is significantly different from a known target value or standard. It's particularly useful when the data isn't normally distributed or has outliers. Why it's important in Six Sigma. It helps to compare the sample median to a target. Very useful when validating goals in the improve phase. It helps define project goals, especially when setting targets that should lie outside the confidence interval. You can also establish baseline performance based on median values when mean isn't reliable. When to use, there are two key situations. 1. When comparing a sample median to a fixed standard to make a conclusion about the population median. 2. For baseline setting, you can use the confidence interval from the one-sample sign test to define baseline metrics. Null and alternate hypotheses. H0. The population median equals the standard. H1. The population median is different from the standard. Examples. 1. Suppose you're testing the mileage of Wagon R cars, and you want to compare the median mileage to Maruti's advertised 14 kilometers per liter. This is a classic one-sample sign test scenario. 2. If your data is in continuous form, like handling time, and you cannot assume normality, you can use the one-sample sign test instead of a t-test to determine whether the median meets a target. You can also use it to set baselines or define goals for future improvements. In summary, use the one-sample sign test when you're dealing with non-normal data and you want to know whether your process median meets or differs from a set benchmark. Mann-Whitney test. Let's now look at the Mann-Whitney test, also known as the Wilcoxon rank sum test. This is a non-parametric test used to compare two independent groups when your data is either ordinal or continuous but non-normal. That means we don't assume the data follows a normal distribution, which makes this a great alternative to the independent two-sample t-test in such cases. When do we use the Mann-Whitney test? When we have two independent groups, such as Region A versus Region B or Group 1 versus Group 2, when the data is not normal or when the variable is ranked or ordinal. When we are comparing distributions or medians between the groups, not the means. Why is this test important? Because it enables us to draw valid conclusions even when our data doesn't meet parametric assumptions, such as normality or equal variances. It's especially useful in business settings where real-world data often has skewness, outliers, or comes from small samples. To summarize, if your project involves comparing the performance or scores of two different groups and you're unsure about normality, the Mann-Whitney test is a powerful tool to apply. Now that we've understood what the Mann-Whitney test is used for, let's review the key assumptions we need to validate before applying this test. 1. Independent random samples. The first assumption is that the two groups being compared are independent of each other, and the observations are randomly selected. There should be no overlap or pairing between the groups. 2. Dependent variable is continuous or ordinal. The variable you are comparing must be either continuous, like revenue, weight, time, or ordinal, such as satisfaction levels or rankings. This test does not apply to purely categorical or nominal data. 3. Similar shape distributions, if testing medians. This one is often overlooked. If we are comparing medians using Mann-Whitney, the two groups should have similarly shaped distributions. If the shapes are very different, for example one skewed left and one skewed right, the test may yield misleading conclusions. To summarize, always check for independent groups, ensure your data is ordinal or continuous, and be cautious about the distribution shapes if your focus is on median comparisons. These conditions ensure the Mann-Whitney test delivers meaningful and reliable results. This slide explains the application of the Mann-Whitney test, which is a non-parametric test used when our data does not follow a normal distribution. Purpose of the test. The Mann-Whitney test is especially helpful when comparing the medians of two independent samples. It's a good alternative when the assumptions for a two-sample t-test are violated, such as non-normality or ordinal data. Unlike parametric tests, this method does not require equal sample sizes and is based on ranking the data, not the actual values. When to use this test when you want to compare whether two independent groups, say Group A and Group B, come from populations with the same median. It helps in testing if one group performs significantly better or worse than the other. Hypotheses. Null hypothesis. H0. The medians of both groups are equal. Alternate hypothesis. H1. The medians of the two groups are different. Examples 1. Comparing the median fuel mileage between two batches of Wagon R cars to check consistency. 2. Comparing the median handling time of two types of customer calls to see if there's a significant performance difference. This test is especially useful in real-world operations where the data doesn't meet parametric assumptions, which is quite common in service processes or small sample environments. This slide provides practical use cases of the Mann-Whitney test, which is a non-parametric test used to compare the medians of two independent groups. It's particularly useful when the data is not normally distributed or when you are working with ordinal or skewed data. Let's walk through the examples provided. Handling time, HT. We may want to compare whether Team A handles calls faster than Team B. If the data is non-normal or has outliers, we compare the median handling times using the Mann-Whitney test instead of using a CE test. Collections. Suppose we ran a collection campaign in March and again in April. We can use the Mann-Whitney test to compare median collections to determine if performance actually improved after the intervention. Cycle time. If we want to test the consistency of two machines or production lines, we can compare their median cycle times. This can reveal whether one line is consistently faster or slower, even if the data isn't normally distributed. Production? Here, we might evaluate the impact of different supervisors on daily production. By comparing the median daily output under Supervisor A and Supervisor B, we can assess if leadership has a statistically significant effect. All these examples share a common theme. We're comparing the medians of two independent groups, and the Mann-Whitney test is ideal when data doesn't meet the assumptions of parametric tests. Moods median test. This slide introduces the Moods median test, a non-parametric test used to compare the medians of two or more independent groups. Unlike parametric tests that assume a normal distribution, Moods median test is ideal for data that may be non-normal, skewed, or contain outliers. Let's highlight when you would use this test. First, it's used when you're dealing with two or more groups and you're specifically interested in the medians, not means. It's valuable when normality assumptions are violated. For example, if your data is heavily skewed or contains extreme values. Unlike other tests, this test focuses purely on median differences, making it robust and simple to interpret when mean-based tests like ANOVA may give misleading results. This test is commonly applied in process improvement scenarios or customer satisfaction surveys where ratings are ordinal, And we want to understand if different teams or time periods lead to statistically different median outcomes. To properly apply the Moods median test, it's important to understand its underlying assumptions. Let's quickly walk through these 3 key points. 1. Independent random samples. The test assumes that the groups being compared are independent of each other. This means that the values in one group do not influence or depend on the values in another. Second, dependent variable is at least ordinal. The Moods median test requires the dependent variable to be measured on at least an ordinal scale. So even if we cannot assume the data is continuous, we need to be able to rank it. 3. Comparison is limited to medians. Unlike other tests that may compare means or full distributions, Moods median test focuses strictly on differences in medians. That makes it useful when we are only interested in central tendency under non-normal conditions or in the presence of outliers. Understanding these assumptions helps ensure the test is applied correctly and the results are reliable. Slide title: Moods median test. Slide purpose. This slide provides a comprehensive explanation of the Moods median test, a non-parametric method used to compare medians from 2 or more independent groups when the data is not normally distributed. Begin by explaining what the Moods median test is. Moods median test is a non-parametric hypothesis test used when we want to compare the medians of 2 or more groups. This test is especially useful when the assumption of normality is violated, making traditional parametric tests like ANOVA inappropriate. Unlike tests that compare means, this test is focused solely on medians, making it more robust when data has outliers or is skewed. Discuss the key points mentioned on the slide. Null hypothesis, H0. All group medians are equal. Alternative hypothesis, H1. At least one group median is significantly different. It assumes that samples are independent and come from populations with similar distribution shapes. While not as powerful as the Kruskal-Wallis test for normally distributed data, Moods test is more robust in the presence of outliers. Highlight practical uses in Six Sigma or other data analysis contexts. This test is excellent in the early phases of analysis, such as the define or measure phase in Six Sigma, where you're exploring data distributions. It helps validate differences when dealing with small samples, skewed data, or situations where variances are not equal. Explain the 3 content blocks at the bottom. Block 1. When to use. Use Moods median test when comparing medians from more than 2 groups. Ideal for non-normal data or data sets with outliers. Block 2. Null and alternate hypotheses. H0. All medians are equal. H1. At least one median is different from the others. Block 3. Example. Example 1. Comparing the median fuel efficiency of more than 2 batches of Wagon R cars. Example 2. Analyzing median handling time across more than 2 call types to see if one is significantly different. Reinforce the note at the bottom. This test is robust to data issues like non-normality and outliers. However, keep in mind that for valid comparisons, the shapes of the distributions being compared should still be similar. Slide title: Moods median test. Use when comparing medians across 3 or more independent groups. Objective of the slide. This slide illustrates real-world examples of when and how to apply the Moods median test. It helps participants relate the test to practical operational scenarios. Begin with a quick recap. Moods median test is a non-parametric test used when we need to compare medians across 3 or more independent groups. It's ideal when our data is skewed, has outliers, or when we are focusing on medians rather than means. Now walk through each example one by one. 1. Handling time, HT. In this example, we're comparing the median handling time across 3 shifts: morning, afternoon, and night. The goal is to determine if one shift is significantly faster or slower than the others. Since the data may not be normally distributed, Moods test is a safer choice over ANOVA. 2. Collections. Here, we use the test to compare collections across 3 different regions or branches. This helps us identify where the collection performance is strongest or weakest. This type of data might have outliers, especially if one region performed exceptionally well or poorly, which makes the Moods test even more relevant. Third cycle time. This use case compares the median cycle time for 3 product types or different machines. It helps in pinpointing variation in efficiency across equipment or product categories. Again, the focus is on the median because means can be skewed by extreme values. 4. Production. Lastly, we compare production output across 3 teams or shifts. The aim here is to analyze which team or shift is consistently meeting or exceeding performance expectations. Using Moods test allows us to analyze performance fairly, despite variability or anomalies in the data. Wrap-up. These examples demonstrate how Moods median test provides a robust method for analyzing real-life performance metrics when you have 3 or more groups and are dealing with non-normal or messy data. Purpose of the slide. This slide provides a consolidated view of 3 non-parametric hypothesis tests, commonly used for centering analysis when the data is not normally distributed. These tests help us analyze median differences rather than means, which is more appropriate when data is skewed or contains outliers. Begin with context. In Six Sigma and other data-driven projects, we often need to evaluate whether a process is centered around a target value. When our data is non-normal, these 3 non-parametric tests, one sample sign, Mann-Whitney, and Moods median, are our go-to options for testing medians instead of means. Column 1. Test. We are covering 3 tests: O1 sample sign test, O Mann-Whitney test, O Moods median test. Column 2. When to use one. One sample sign, O. Use this when you want to compare the median of a single sample to a fixed standard, like a benchmark or historical target. O. It's also useful for setting baselines using confidence intervals when data is continuous but not normal. Second Mann-Whitney. O. This test is applicable when you want to compare the medians of 2 independent groups, commonly used when you have 2 sample groups and non-normal distribution. 3. Moods median. O. When comparing medians across more than 2 groups, especially under column 3, HO and HA, null and alternate hypothesis. Each row outlines the respective null and alternate hypotheses. O1 sample sign. Ho, median equals the standard. Ha, median is not equal. O Mann-Whitney. Ho, medians of both groups are equal. Ha, medians are different. O Moods median. Ho, all sample medians are equal. Ha, at least one differs. Column 4. Example. Practical illustrations are provided for each test. O1 sample sign. 1. Checking if a batch of Wagon R cars meets the advertised fuel efficiency of 14 km per liter. 2. Using it to define a baseline for process handling time. O Mann-Whitney. 1. Comparing median mileage between 2 batches. 2. Comparing median handling time between 2 call types. O Moods median. 1. Comparing mileage across multiple batches. 2. Analyzing median handling time across more than 2 call categories.